not interested in. Okay, you talk.
Okay. Good. So since, again, in this chapter, we're talking about applications of integrals to various different subjects, and in last meeting and this meeting, I've been giving kind of just an assortment of places where integrals are used in science, specifically physics and physical chemistry and thermodynamics. So today we're going to continue with that topic. I want to just go through really quickly again the two main things we did last time, which were deriving the ideal gas law and understanding work. We'll extend our understanding of work to the case with potentials in Act 1. Then I want to talk about another application to physics for objects which have non-constant density. So the density changes from point to point, so you can handle that with an integral, and closely related are center of mass and moment of inertia. And then at the end I want to do a couple more things about gases and thermodynamics, partially related to what you were doing with the van der Waals gas and the work done by integrating PDV. So kind of disjoint unrelated topics, but hopefully it'll give you a deeper appreciation of where integrals are useful. So good. Before the review, thoughts on any of this?
So you're telling me that integrals are useful in physics?
Well, obviously, I mean, if you open any physics textbook, it's all integrals. I mean, to say integrals are useful in physics is probably a misnomer. Integrals are the thing which physics concerns itself with, basically.
Oh yeah, I guess that's literally the man who invented calculus was a physicist.
Yeah, Newton literally came up with the derivative and integral, machinery precisely in order to solve problems about like understanding how an apple falls or how the Earth moves around the sun. So like, yeah, you're right. Calculus was literally invented by a physicist to do physics. Like there's a very deep sense in which just teaching calculus without physics or physics without calculus is kind of meaningless because they're really just two parts of the same field.
Lovely. Oh great, is this part of your convincing me to go into physics rather than chemistry?
Well, no, I mean, that will come in time. But all of this, I think, is equally applicable to, physical chemistry or thermochemistry as well as physics. So I'm still being quite agnostic as to what you ultimately want to do.
Lovely.
Okay, so quick, what did we do last time? I just want to outline the major steps since this was a very involved calculation. It's easy to get lost. So what we did was this example of a very general recipe called the microcanonical ensemble that you can use in many, many systems, although in real life you actually use the canonical ensemble more often. But anyway, I'll tell you what the microcanonical ensemble is, and we'll discuss the other one a little later when we do probability. But basically the steps are as follows. You start with any physical system that has some energy. Some way of describing the energy. So for instance, if you have an ideal gas of particles in a box, the total energy is simply the sum of the 1/2 mp squareds for all of the little gas particles. Okay, fine. Then you simply say, okay, fix a particular energy E, and now count the number of microstates, the number of configurations of the system that have the same physical energy. So if the system is discrete, like spins that can either be up or down, this counting is actually a counting. If there are continuous parameters like a velocity, as there is in the ideal gas, when I say count, I really mean an integral, which is a phase-based volume that's, some continuous count. But okay, fine. So you do that counting. You count how many microstates have a given energy. Then the critical Boltzmann bridge step is we relate this macroscopic quantity called the entropy to this microscopic quantity, the number of microstates, by the equation S is kb log omega. And then the laws of thermodynamics, everything up here so far has been basically statistical mechanics. So the relationship between statistical mechanics and thermal physics or thermodynamics is then to use the laws of thermodynamics to turn our knowledge about entropy into knowledge about physical properties. And we did that last time to write down this P is T ds dv, and once we knew what S was, you just take a derivative, and this gave us PV equals nRT. Right, so that came out of this formula that we got for the entropy when we took a derivative with respect to V. This log turned into basically an n over V times 1 over n, which is a 1 over V. So basically T kb n over V is P, which is the ideal gas law. Good. So we did that last time to see how StatMech works. And in a sort of orthogonal direction, I motivated this question of what happens if you start with Newton's second law, F is md v dt, and integrate both sides over x. So you integrate both sides with respect to x. And then we did some changes of variables and showed that the right side turns into this very nice form, which is the difference in this quantity that looks like 1/2 mv squared. So I did this to show you that this 1/2 mv squared that is often in high school courses written down and pulled out of someone's asshole without any justification, it comes out in a very natural way from just taking the integral of the force and asking, what is that? So then we just attached some words to that calculation. We attached the word work to the left side, the integral of the force over a distance. And then we attach the words, change in kinetic energy or delta KE or whatever to the right side. So I think it's just very important not to get too caught up in words and equations that are handed to you, right? You should know that they all come from somewhere. So that was last time. So have I brought any questions to the front of your mind in the review of what we discussed last time? Are you muted?
Why, yes, I am. There's a note I need to take down.
There's a note, you said?
Yes.
What is the note?
Tell you later.
Oh, okay. I can't tell. Oh, all right. Well, I guess you don't want to say. So, good. Okay, so let's do some more with work. Okay. So just as a warm-up question for you, using that expression for the work as the integral of the force from before, let's think of our favorite example like a point particle or a ball that's falling under the influence of gravity. So there's a ball with mass m, and it experiences some downwards force. That arrow is not very straight. Some downward force. F is minus mg, so minus indicates it points downward. So if you fall from an initial height y0 to a final height y, I'll ask you, it's not terribly difficult, how much work is done on the ball?
So I believe we are integrating negative mg with respect to m.
M? Why?
Well, let me see.
You say integrate with respect to the mass? What does that mean?
Okay, I was not aware if that was mass for meters.
No, m for mass. Mass times
Okay.
acceleration due to gravity.
Let's say dx.
Yeah, sure. I mean, you could just call this the x-axis, even though we're labeling the y's or whatever. But okay, so
Because we already have a final height y and it'd be...
Yeah, you don't want to conflate variables dy and have the y here. Okay, good. So
Yeah.
that's the work. What are the bounds of integration?
Let's see. Y0 at the lower, y at the higher.
Good, and that's the easiest one in the book, so what does that come out to?
Negative mgx, big boy surrounding it at y0, or mg times y minus y0 in parentheses.
Yeah, minus mg times y minus y0. Good. So you might want to move the minus sign in and switch the order just to make it easier, because we know it starts at a higher y0 and ends at a lower y, so we know y0 minus y is positive. So I just moved the minus sign in to make that clear. Good. Okay, so that's it. That's the work done. As I just signaled, since y0 minus y is positive, the work done is also positive, which makes sense, right? Because we know that the work is supposed to be the change in kinetic energy, and we certainly expect that as the ball falls, it's starting to move faster and faster, so its kinetic energy should increase. And by the WorkEnergy theorem, you therefore expect the work to be positive. And it is. Good. Okay, so that's quite easy as a warm-up. But now let's just observe a pattern that we've seen in several problems where we've done this before. So I've rewritten the WorkEnergy theorem here to remind us again. And I just want to review a couple examples of the force function on the left side that we've integrated. So last time we did this...
Oh, may I interject?
Yeah, please do.
We were in lab earlier at Lehigh, and Professor Lanscombe mentioned what I'll call a variation of the kinetic. Well, it's basically directly related to WorkEnergy theorem, but half charge times voltage squared.
Half charge times voltage squared. This is not something with units of energy.
Let's see.
Are you talking about capacitance? A capacitor and a circuit?
Yes, the capacitance formula.
That's different. Yeah, capacitance. Yeah, okay. And have CV squared. Yeah, so How did this come
I'm
up?
just, oh yeah, it would be, it just showed up because we were talking, well, I think. I think we were discussing calculating the capacitance of this carbon plate of interest.
Yeah, we could discuss that as well. That's
But I just felt the need to mention that
yeah.
it appeared very similar to what we see from the work energy theorem, just based off of the 1/2 thing to first power, thing to second power.
Yeah, this expression comes up again and again in energy type expressions. Like the reason it happens in a capacitor, I mean, a capacitor is just some shape where you store some net charge on it, Q, and then it develops some potential difference V between it. If I remember correctly, I think V is supposed, or the capacitance is defined as, is it the voltage per unit charge or the other way around? Capacitance is measured in farads. And then the energy is supposed to be, normally you would say this is QV, but then you could replace V is CQ or something. So this is supposed to be proportional to, if I remember correctly, CV squared, which is close to what you were saying. Depending, if it's a parallel plate capacitor, this would be related to the length. But yeah, this is it's closely related because a capacitor is just something which is storing energy in some electric field, which we discussed yesterday.
Just random thoughts. I don't know.
Yeah, it's good. It's good that you're making connections between the different types of work that you're doing. Good. Okay. But back to the work energy theorem in classical mechanics. Okay, so last time we did the spring force, so F is minus kx, and we explicitly were able to compute the integral on the left side to get this, you know, this thing that looks like 1/2 mv squared, but now it's 1/2 kx squared or something. So in this case, you can do the integral, and it's the difference of some function evaluated at two endpoints, right? Then we did, or you did in a DC, the Coulomb force, and again, you can just do the integral, and it's the difference of some function at the top and bottom endpoints. Okay, good, that makes sense. That's how integrals work. As we just did in the third case, you integrated a constant function, and again, you could write it as some function evaluated at a top and bottom endpoint with no integral involved. So, of course, the reason why this integral turns into a difference of a function at the top and bottom is just by the fundamental theorem of calculus, but it raises an interesting question. Could we re-express the left side of this equation in a simpler way if you could find a function, maybe a function, well, we're going to change the sign in a second, but imagine you could find a function u of x with the property that the derivative of u with respect to x is f. Imagine you could find that. So you can find an antiderivative for the force. If you could find such a function, the work energy theorem would no longer involve an integral at all, because you would just use the fundamental theorem of calculus to kill this integral, right? The integral of a derivative is just the function evaluated at the endpoints. U at xb minus u at xa. And then you would move these to the right-hand side, which has the kinetic energy. So then the equation would become 0 equals basically kinetic energy at B minus the kinetic energy at A. And now I'm going to move this to the other side. It'll be plus the potential, as we call it, this function U at A, minus, since we have to move this to the other side, the potential at B. So if you could find a function which is an antiderivative of the force, you could write the work energy theorem in this new way. But now you're looking at this and you probably say, okay, this isn't very satisfying, because the first two terms are kinetic energy at B minus kinetic energy at A. But then the last two terms are U at A minus U at B. The order is switched. So you might say, that's not very satisfying. I would like this to be two different quantities that are evaluated at B minus evaluated at A. Right? I want it to be B minus A, B minus A. So I could interpret this as, you know, the sum of some total quantity at B minus the sum at some other A. So that's very easy to fix. All we do is go back to our definition at the beginning and say, okay, I don't want to find a function whose derivative is f. I want to find a function such that minus its derivative is f. Why is that useful? Well, now I just track through and include a minus sign at all these points. So now there's a minus sign here. This turns into a plus sign, and then our final equation gets fixed into the form that we wanted. So it will be now plus, minus the potential at A plus the potential at B. And now this is very nice, because the bottom equation is saying that 0 equals the kinetic energy plus the potential energy at B minus the kinetic energy plus the potential energy at A. Okay, so that's the idea. The idea is we just want to say, is it possible to find a function whose negative derivative is the force? So here, let me say that again. If, again, you could find such a function u so that f is minus du dx, then by the fundamental theorem, you would just evaluate the left side of the work energy theorem, get this thing, and then you would move it to the right side. And then you would say, okay, this is a conservation law. What do I mean by conservation? I mean, this is telling you that there's a particular sum of two quantities. The sum is you add up the kinetic energy at B and the kinetic energy and the potential energy at B, and that thing has to be equal to the sum of the same two quantities, the kinetic energy at A and the potential energy at A. Or in other words, this is telling you that the sum of the kinetic and potential energies always stays the same, right? Between any points A and B, the sum of kinetic and potential is unchanged. So when something is unchanged in physics, we say that it's conserved, or a conservation law. Okay, so this is very powerful. This is a better version of the work energy theorem, because instead of saying some integral equals the change in some quantity, now we've written it as some quantity, kinetic plus potential, is conserved. It stays the same.
I mean, it's not powerful yet. We haven't written down what u is.
Yeah, but that's, I mean, u will be different in different systems, right? I mean, let's just look at those examples we did before. In the three cases that you told me how to solve before, well, the potential energy for the spring force is a half kx squared. The potential energy for a charge, which you already know from 309.1, is basically kq1, q2 over r. The potential energy for the gravitational force, u, is basically mgy, because you take a derivative, a minus derivative, and it's supposed to be this. So we can basically read off from our previous results. We already know the potential in these three cases, and you can now imagine it's not so hard to find the potential in a bunch of other cases, right? Does that make sense?
Yes.
Good, good, good. Let me just emphasize one thing. You can't always do this. So if there exists a function u such that the force is minus du dx, then the force is said to be conservative. It means there's some conserved energy. That's not always true. An obvious example is friction. If you roll a ball and friction acts on it, it's going to slow down and eventually stop. So the kinetic energy at the beginning is non-zero, it's moving. The kinetic energy at the end is zero, it's stopped. And it didn't gain any potential somehow. So friction does not conserve energy. Viscosity or drag for a projectile moving through air is also not conservative. So this isn't always true, but if it's true that you can find such a function, then f is conservative. Okay, so now that we know what the definition of potential is, we can explain some seemingly confusing statements that are often made in chemistry courses, or even high school biology courses when you talk about enzymes or something. So I'm going to rant a little bit, but I always thought that this was very frustrating, that in science courses in high school, I would be shown some diagram like this, some potential energy diagram, and I would be told, particles always try to minimize their potential energy, or particles always move to the minimum of a potential. And this would be stated as though it were some deep philosophical notion or something, right? Like, I don't know, particles are lazy, they always want the minimal energy. And you would ask, okay, why is that true? And people would never be able to answer you. They'd just say, that's just how it is. Particles minimize their potential energy.
That's just how it is. Oh boy.
Yeah, it's the worst fucking answer in the book. That's just how it is. Now we have a much better answer. You can ask, why do particles move towards a minimum of the potential? It's literally just because force is minus the derivative of the potential. So just look at all the cases. If the potential is sloping downwards, the derivative is negative. That means minus the derivative is positive. So the force is positive, and the particle moves to the right. Okay, what if the slope is positive? If the slope is positive, minus the slope is negative, so the force is negative, and the particle moves to the left. What if the slope is zero? If the slope is zero at the bottom, minus zero is still zero, so the particle feels no force, right? So it's very, very simple. the question of why do particles move towards a minimum of a potential, it's not some deep philosophical thing. It's literally the fucking definition of potential. They feel a force that are pointing them opposite the direction of the slope. So if the slope is negative, it goes towards positive, and if the slope is positive, it goes back towards negative. And that's why it moves to a minimum, right? Because the minimum is the place where the slope is 0. This is called a stable equilibrium, as opposed to an unstable equilibrium over here. Because if you're sitting at the top of this hill and you get kicked a little bit, you're going to fall away, so it's unstable. Okay, so I just want to hammer this home. The statement that particles minimize their potential is not fucking magic. It's the definition. It's just a derivative. Okay, that's one rant. Is there another rant that I wanted? Shit, what was the other rant? Maybe I had it.
What was the other rant I wanted to make? Welcome to Minutes.
I have a lot of rants. There's another thing that people say about energy. Oh yeah, well, people ask like, why is energy conserved or something, and act like conservation of energy is some mysterious property. But I mean, that's not magic either, because we literally just defined this thing as a derivative so that this sum would stay the same in time. So hopefully, the statement that energy is conserved is also not some magical God-given thing that was handed down, because we just proved it. We just defined what energy was, so that we could do this integral and write some quantity which doesn't change. So yeah, two things. Particles minimize their energy, obvious. Energy is conserved if there exists such a function u, also obvious, just by the WorkEnergy theorem. Okay, so now I'll ask you, this problem actually doesn't involve any calculus. It's just, now that we know energy is conserved, you can just write down energy at the beginning and energy at the end and just do algebra. So let me describe the setup for you. There's a bead of mass m, so here's the mass m, and it slides without friction, so no friction, so energy is conserved, on a hoop of radius r. This should be lowercase r, actually. So it slides on this hoop of radius r. Now, the bead has both some response to gravity, so it feels the force due to gravity, and it has a spring at the bottom of the hoop. So let's just remember the potential energy for those two things. So the potential energy due to gravity was supposed to be mgy, right? So minus the derivative is force is minus mg. And the potential energy from a spring was supposed to be 1/2 kx squared. Why is that? Because the spring force is minus kx, and minus the derivative of this is indeed minus kx. So I claim that the sum of these two potential energies and the kinetic energy will be conserved. Okay, so how do we use that? Well, the question is, assuming that the equilibrium length of the spring is 0, so that means that this potential energy for the spring means that we're supposed to use the stretched distance x, which is the distance from the bottom where the spring is attached to where the mass is. So the x in this thing is the length of the spring, so that's fine. You assume that that equilibrium length is 0, and that the bead is released at the top of the hoop with basically no speed, 0 speed. The question is how fast, so what is the velocity of the bead when it hits the bottom of the hoop? So we're going to use energy conservation to do that. For some reason here, now the radius has changed from lowercase r to capital R for some reason. Oh, no, that's fine. No. It's, sorry, lowercase r is the length of the, from here to the spring. So it is true that the radius of the hoop is capital R. Okay. So anyway, all right, so I'll ask you, what equation should I write down to express energy conservation between the beginning, where it's at the top, and the end, where it's at the bottom?
Sorry, could you state the final question again?
I'm asking you, what equation should I write down to express conservation of energy between the beginning and final states? Let's start with the beginning. So what's the energy?
Let me guess. It was supposed to take me 5 seconds.
Well, it shouldn't be hard. Well, what's the energy at the top? So when this thing starts all the way at the top of the hoop, what is its total energy?
I guess both that combination of the... Is it the... Okay. I'm going to guess that is the addition of the gravitational potential energy and the energy of the spring somehow. But that is a guess.
Yeah, no, that's correct. It's not a guess. I told you that was true. I told you at the beginning that since it feels gravity and the spring force, the potential energy is the sum of these. So sure, that's fine. So what is that sum equal to when this guy's at the top?
I have no idea what UG is supposed to be.
This is the potential energy due to gravity, and this is the potential energy due to the spring. Right?
Oh, the lower one is actually S, not screwed up G.
No. So this should be a spring. So
Okay.
potential energy spring, potential energy for gravity.
So U total equals MGY plus. Well, am I?
Well, you have to tell me what Y is.
That is the force.
No, it's not the force. This is the potential.
Let's see. We're putting into each of these for Y and X, I believe 2R.
Yeah, good.
I mean, yeah.
Because at the beginning,
So,
indeed, the height, so the Y, which I put into the gravitational potential, is 2R, because he's all the way at the top. And also the length of the spring is 2R, so X is 2R. Good, so that's...
okay, so U total equals mg2r plus 1/2 k, begin in parentheses 2r squared.
Yeah, so 2R quantity squared, and we can simplify that a little bit. So that's just 2 mgr plus 2 squared is 4, so 2kr squared. And that's actually the total energy, including both potential and kinetic, because there's no kinetic energy at the top. Negligible speed, so V is 0 at the top. Okay, so now what's the total energy at the bottom? So when it's all the way, falls to the bottom of the hoop, basically.
So at the bottom, all the potential energy is converted into kinetic energy, if I'm not mistaken.
Yeah, because Y is 0 and X is 0, because it's all the way at the bottom. So what's the total energy?
So is this integrating from 2R to 0 of each of these?
No,
okay.
No integral.
No.
Energy is kinetic plus potential. There's no potential, so the energy at the bottom is just kinetic. So what's the kinetic energy?
Am I supposed to be trying to consult myself for... Well, there's...
I mean, this thing slides to the bottom of the hoop, and then when it hits the bottom of the hoop, it's moving with some speed, with some speed v. So the kinetic energy is 1/2 mv squared, right? That's it.
Okay, so we don't need to solve for what v is?
That's what we're trying to do, right? We're going to set EI equal to EF and solve for v. I mean, this is what you do in any problem. When you want to solve a problem, you define a variable for the thing you want to solve, you find an equation that variable satisfies, then you solve the equation, right?
Okay, so you want to find the kinetic, set it equal to kinetic energy, and then solve for the velocity.
Yeah.
Okay.
Good, so we're conserving energy between the top and bottom, so I should set EI equal to EF, right, because there's no friction. So when I do that, I have, what, 2 mgr plus 2, my handwriting's getting a little bad, but kr squared, my k looks like my r, is 1/2 mv squared. Now just do some algebra for me. What is the velocity at the bottom?
Let's see, velocity is equal to the square root of 4 mgr plus 2 kr squared over m.
Yeah, so in the first term the m cancels, so it'll just be 4 gr. In the second term there's a k over m. So it'll be 4 times kr squared over m. Good. So that's it, that's the answer. I find this very satisfying, because now, I mean, we just know how fast this thing is going to be moving at the bottom, and we never had to do any integrals, we never had to write F equals ma. It was purely an energy conservation argument. I mean, there were integrals behind the scenes that went into the WorkEnergy Theorem, but this seemingly challenging problem of finding how fast is this moving at the bottom just turned into algebra. Right, so let's see that one more time. As you told me, the initial potential energy, since it's at height 2r, is 2 mgr. the spring potential energy was a half K times 2R quantity squared. 2 squared is 4, so that's 2KR squared. Initial kinetic energy is 0. Final kinetic, why did I say this? Final potential energy is what I should have said. The final potential energy at the bottom is 0, because it's at 0 height, and the spring is not stretched. So our conservation equation is 2mgr plus 2kr squared is a half mv squared, or v final squared if you prefer. And when you solve, I pulled out the 4s to get an overall factor of 2, but besides that I think this is the same. The velocity is just 2 times the root of gr plus kr squared over m. Good, good. And all of the units work out. G is meters per second squared, so G times R is meters squared per second squared. Square root of meters squared per second squared is meters per second, so that's good. In the second term, the spring constant K, well, F is Kx, so K is newtons per meter. So Newton is a kilogram meter per second squared. So a K, that per meter, would be kilograms per second squared. Kilograms per second squared over kilograms is just per second squared. And per second squared times meter squared is meter squared per second squared. And the square root of that is back to meters per second. So units are beautiful, everything works out. This is the correct answer. Very cute, I think. Okay, good. Thoughts, questions, concerns about that?
Nope.
Okay. This is like a grown-up physics problem or something that you would do in an actual physics course. So, okay, nice. Let's do some unrelated stuff. So, density and center of mass and moment of inertia. So, let's try to just motivate the formula we're going to write down for density. So suppose you wanted to get the total mass of a collection of discrete point masses. So you just have a bunch of point masses on the line, M1, M2, M3, M4, M5. The way to get the total mass is fairly obvious, right? You simply add up sum from I equals 1 to 5 of all of the mi's, which is the sum of all of these. So this is all you do. You add up masses. So that's one answer. This gives us the answer for the total mass of a system that is discrete. On the other hand, you know from chemistry or just common sense that if you wanted to find the total mass of like some block, maybe there's a block of wood with some density, or maybe it's a cube filled with water, and water has a density of like 1 gram per cubic centimeter or something. If you want to get the total mass and you know the density, you multiply it by the volume, so maybe this is 1 cubic centimeter, and you would say now the total mass of this thing is 1 gram. So we know two different things. We know how to get the total mass of a system that has many different discrete masses, and we know how to get the total mass of a system that is continuous but has some constant density. Oops, this one's the density. Constant density everywhere. But what we don't know how to do is how do you find the mass of an object whose density changes? So I'll use the letter rho usually for density. Maybe you have some cube where it's very dense in one corner, like 10 grams per cubic centimeter, and way less dense, like 0.1 grams per cubic centimeter in another corner. You could just ask, how do you find the total volume of such an object, right? This is not something you normally study how to do. But we can do it with integrals now. So here's the way to do it. Suppose, for a concrete example, suppose we have some rod, so it's some one-dimensional object. And you know its density, its linear density. So I'll use the letter lambda for linear density. The units of lambda would be something like grams per meter, right? So it's a density per length, right? So we want to ask, what is the total mass of this whole rod, right? So you do what you normally do in calculus, which is to say, well, I don't know how to find the density of something, or the mass of something whose density is changing, but I would know how to do it if this were a bunch of discrete point masses, the way that we did before. So what I'll do is I'll just chop up this rod into tiny pieces, so tiny that the density is approximately constant on each of those little chunks, and then I'll just add up the masses from each of these chunks as though they were discrete point masses. So what would that look like? Well, I mean, this chunk in the middle here, this P3, would be roughly the density function, which is lambda, evaluated at this point, x3, So lambda evaluated at x3, that gives me a density in grams per meter. So to get a mass, I better multiply it by a length in meters, but the length of this chunk is delta x. Right, and similarly, the mass of this little guy over here, this would be lambda at x1, delta x. So the total mass m, is supposed to be, I guess, the sum of all those little discrete masses from maybe I equals 1 to n of lambda evaluated at xi times delta xi. Or if you prefer, as I've written it over here, instead of delta xi, you could just have it as the difference, xi minus 1. Right, like instead of delta x, I could just say this is x2 minus x1, this length here. Okay, well that's fine. That sum is just an approximation, but now is where the magic happens. Because we saw when we proved that the Riemann integral is equivalent to the Darboux integral, that if you take the limit as delta x goes to 0, or equivalently the limit as the number of points in this partition goes to infinity, we proved that that's the same as the usual definition of the integral, which we defined as the supremum of lower sums being equal to the infimum of upper sums. So whenever you have something with this property and you take the limit as the number of points goes to infinity, you can replace that sum by an integral. So we've now effectively proven in a sort of hand-waving way the total mass of a rod whose density is changing with some density function lambda. The total mass is just the integral of that density function over x. And now you see why people, especially in science, like this little placeholder dx, because this is formally meaningless, right? Formally meaningless. Dx doesn't tell you anything except the variable you're integrating with respect to. But if you're a scientist, it's very helpful for checking the units of an equation like this, because the units of lambda are supposed to be something like grams per meter. And mathematically, when you integrate something that has units of grams per meter over a distance in meters, it cancels one factor of meters downstairs. So as a mnemonic, to help you remember that this integral over length cancels that factor of meters downstairs, you could pretend that this placeholder dx actually secretly has units of meters. Right? It's not actually true, dx is meaningless, but if you think of it as this thing somehow came from an approximate sum where lambda was multiplied by some delta x's with units of meters, if you think of it that way, you could say, oh, so dx is somehow carrying a unit of meters, which cancels this, so I'm left with some mass in grams. Not actually true, just a mnemonic. I mean, the correct answer is just to say when you integrate over a length, that integral gives you units of length, but whatever, this is kind of cute. Okay, good. Thoughts on this, or is this all totally obvious?
As I spend 15 seconds trying to unmute myself, I do not have any thoughts.
Okay. All right, onward to examples then. So let's just do some integrals. How would you find the total mass of that rod on the previous slide? Well, I told you that the density was supposed to be some lambda 0 times x over L. So you just do this integral. You do the integral of basically lambda 0 x over L. You can pull the constants out of the integral. So this is the integral, well, lambda 0 over L times the integral from 0 to L of x. But that's a half x squared evaluated at L and 0, or just a half L squared. So that L squared over L gives me a net factor of 1L upstairs. So my total answer for the mass is 1/2 L lambda 0. So notice this is different than if the rod just had constant density lambda, then the total mass would have been lambda times the length. But since it's changing, you get a half lambda times the length. Okay, so that's a linear example. Often in problems you study a system that has a density not in kilograms per meter or grams per meter, but something called an area density. So an area density is a number which describes a two-dimensional object like a thin disk or something. So a two-dimensional disk, and that disk maybe has some density in grams per square meter. So this is some density that you multiply by an area to get a mass.
Is this only meaningful when it comes to integrals?
No, this is a totally meaningful quantity physically as well. Like if you have a sheet of paper, you might approximate it by saying that the sheet of paper has some density per unit area, right? And then you cut out some area of the paper and weigh it and say, okay, that's going to give me its area density. So no, this is used.
I mean, you're not wrong.
Yeah, no, I mean this is a useful thing. This comes up quite a lot. Okay, so you could say, all right, can I find the total mass of, some two-dimensional object that has radially varying area density? So maybe I have some disk in the plane with some total radius r, and it has some density which is given by this, maybe some exponential. So sigma is some number sigma 0 times the exponential of r squared over capital R squared. How do you do that? Well, as usual, when you want to do some integral over this disk, you should chop it up into circles. So if I chop this up into circles, each of these circles, well, you can think of it if you like as a very thin ring or something. So the area of this very thin ring, if the difference between the radii is like dr or something, you would say that, well, this is 2 pi r, the circumference of the circle, dr is supposed to be the area. Right, so basically you just chop this disk into thin rings and then say, okay, well this is some area, 2 pi r dr is somehow this area of this thin ring. So this is the area, and now I multiply that by the area density, sigma at r, and if I somehow add up all those contributions, which turns into an integral, I get the total mass. So, okay, sure, let's do that integral. It's pretty easy. You could probably see either by u substitution or just by guessing what it has to be. We can pull out all the constants. So sigma 0 and 2 pi are constants that all go outside. And then you just ask, what is the integral of r e to the r squared over r squared? Well, we know the derivative of e to the r squared over r squared would be e to the r squared over r squared times 2r over r squared. But there's a 1r here. So the integral of this thing is going to be 1/2 times capital R squared, to kill the factor downstairs, times e to the lowercase r squared over capital R squared. Or you could just do the u sub u is r squared, du is 2r dr, if you prefer. Whatever. Okay, so whatever. Either way you do that, the 1/2 kills this 2. You have a pi sigma 0 outside. And then inside you have this r squared, capital R squared, e to the lowercase r squared over r squared, evaluated at r and 0. At the top, when you plug in capital R, this is e to the 1, which is e. At the bottom, when you plug in 0, this is e to the 0, which is 1. And I can pull out the r squared. So the total mass is a bunch of constants, pi sigma 0 r squared, times this number, e minus 1, right, which is like 1.718 or something. So, okay, cute example, but it's just integrating over a circle by a disk by chopping it into circles. Okay, questions on density integrals?
No.
Good. Okay, onward to center of mass then. So in the same way, I'll start with discrete point masses. So let's just do the easy case. If you have 2 point masses m1 and m2, we would like to define the center of mass for those point masses, which is going to be basically the weighted average of their positions x. So if the smaller one is at x1 and the bigger one is at x2, then the center of mass is going to be the weighted average of x1 and x2, where the weights are the masses of the particles. So in other words, the center of mass is mass 1 times position x1 plus mass 2 divided by position x2 divided by the total mass. So this is a weighted average in the same sense that, some maybe grade. You have some grade, which is a weighted average of like, 0.5 times a test score plus, 0.1 times a homework score or something, plus ... all over, the sum of these weights. So like 0.4 plus 0.1 plus ... the bottom should add up to 1. This is just a weighted average where you are averaging these different grades like test and homework and whatever, but you're averaging them in an asymmetric way, where some of them have larger weights, like 0.4 as opposed to 0.1. Except here the weights are m1 and m2. Okay, good. So the center of mass should it's not going to be exactly in between these two particles. It's going to somehow prefer, it's going to be closer to the larger mass. So that's simple enough when you have just two particles, and hopefully it's intuitive how this thing generalizes when you have some collection of particles. So if you have many masses mi, you just do the same thing. So you add up all of the mass times its position in x. So m1x1, m2x3, m2x2, m3x3, m4x4, and so forth. You add up all of those, that weighted average, and divide by the total mass, where again, by total mass, I just mean the sum of the mi's from I equals 1 to n, just sum of the masses. Okay, sure. So weighted average, it's very simple. This is again in the discrete case. But hopefully now it's kind of intuitive how this is going to go over to the continuous case, because we're just going to play the same game about chopping our continuous mass into little chunks, doing this sum, and then turning the sum into an integral. So what do I mean by that? If we again have some rod, so you have some one-dimensional object where each of these chunks has some tiny, if this is at xi, each of these guys has some mass mi, which is supposed to be the density lambda at xi times some width delta x. If that's true, maybe delta xi or something. So if that's true, what I should really do is add up, well, again, what I want to do is basically add up all of the positions x times the masses, which here I'm writing delta m, or in other words, delta m could be lambda times delta x. In the limit, as we take the little masses very, very small, delta m's go to 0, we can write the top as the integral of, well, this becomes an x, this is integrated dm, but it's more useful to change variables and not do the integral dm, but to change to dx, dx using the relation dm is lambda of x dx. So I replace the dm by density times dx, and that gives us this expression. So the center of mass is another integral. It's the integral of x times the density. So now it's not just the density itself, but it's the position times the density, integrated over x. And you again divide by the total mass m. But just to remind us how you find the total mass m, the total mass is the integral of the density. So this thing looks kind of funny. The numerator is integral of x times density, the denominator is just integral of density. Right? That's the center of mass position. Okay, that was for a rod, but you can see pretty easily how this will generalize if you have some three-dimensional object. The y center of mass is just going to be integral of y lambda, maybe, I don't know, d3x or something if you're in 3 dimensions over the total mass. The z coordinate of the center of mass is going to be an integral of z times lambda d3x, where now lambda is some mass per volume all over m, and often we collect this into a vector. So the vector center of mass is x, y center of mass, and z center of mass. Okay. Good. Still pretty simple. It's just a weighted average, but now in an integral. So let's go back to that rod example. So suppose you want to find the center of mass of this rod, where now basically this is something where the density is 0 on one end, and the density gets larger and larger until the density is lambda 0, some finite density at the other end. So it's increasing. So we expect the center of mass to be to the right of the middle, right? Because it's not right in the middle, because the right side is heavier than the left side. So let's see if that comes out. As we said, we integrate x times the density. I guess there should be a dx here. So integrate x times the density and divide by the total mass, which we found before. I'm going to pull out that total mass. Since we had a 1/2 downstairs, that turns into 2 upstairs. So the overall prefactor is 2 over L times lambda 0. We integrate x times lambda. Lambda is lambda 0 x over L. So these 2 x's give us an x squared, and we're left with the lambda 0 over L from the density. I'm going to pull out this factor because that kills this thing. Well, kills that thing, maybe not in the next step, but eventually. and I integrate x cubed, which gives me a 1/3, or sorry, x squared, which gives me a 1/3 x cubed, evaluated at 0 and L. 0 gives me nothing, so I have a 1/3 L cubed. And now in the last step, I see I have 2 factors of L downstairs and 3 factors of L upstairs, so I'm left with 2/3 L. Good, so the units make sense. The center of mass is at a length of particular distance, and we see that if this thing had total length L, then the center of mass, which we usually write with like an X marks the spot or something, so the center of mass is at this 2/3 L. So it's closer to the right side because the right side is heavier. Good, easy example, but okay. Questions on this thing?
I don't believe I have any questions, but is on slide 22 there going to be a challenge?
No, I don't think so. I've not too many challenges today, actually.
Okay, because I was like, oh god, there's an example. That means that the next one must be a challenge.
Now, I realize that if I want to cram a bunch of stuff in, I should go faster and do the work for you. So, a lot of examples today.
Okay.
Yeah, actually the next slide is an example where I was lazy and just took a screenshot directly out of a textbook. So here's an area example, but by symmetry it actually turns out to be easier. So the question asks us to find the center of mass of a semicircular plate of radius r. So we assume, since density was not given, that the density is constant. So I would write that as some area density, sigma of x equals sigma, which is constant, although they won't use that letter here. Okay, so here's the picture. It's a semicircle of radius r. We want to find the center of mass. So technically speaking, you would need an x center of mass, which is, integral of x sigma over integral of sigma, and a y center of mass, which is integral of y sigma over integral sigma. But you can kind of see just by looking at the picture that by symmetry, the x position of the center of mass has to lie about this axis on x equals 0. There's no way the center of mass could be on one side rather than the other, because the figure is symmetric under this C2 that rotates by 180 degrees about the y-axis. So there's no way the center of mass could be anywhere off of this line, because then the center of mass would move when I applied the symmetry transformation. But we know the whole picture has to stay the same when you apply a symmetry transformation by the definition of symmetry. So actually that makes the problem much easier, because you don't have to find the x part of the center of mass, you just find the y part. So we'll just do that. Okay, so let's find the y part. They don't use the letter sigma here, but in their notation, y bar, which is y center of mass, is supposed to be, I guess, 1 over the total mass, but they're using area, so I guess they're pretending that the density is 1. Right, except the density is 1, then the total mass would be 1 times the area, or just the area. Or you could just think of this as having a sigma upstairs and a sigma downstairs, and they cancel. So the downstairs are just left with area. So anyway, fine. So this is 1 over the area times, well, what are we supposed to integrate? We're supposed to integrate, I guess, y times the density near that point. But here they're assuming the density is 1, or again, if you prefer, that the density is canceled out. So we should really just be integrating these y's, basically, the y position, as we run from 0 up to r. Okay, but here, wait, is that true? F of x, why is it squared? I've confused myself. So y would be square root of r squared minus x squared, but they're squaring it because, why have I confused myself? This should be the integral of y times sigma dy, right? Y. Oh, right, because, okay, sorry, I'm confusing myself, because we're integrating up on y's, but for each of those fixed y's, to get the total area is going to be the length of this slice times our little change in y dy. Right, so if we're integrating along y, we're not just integrating y, we're integrating y times these slices, right? So when we integrate up these slices, we have one factor of the square root of r squared minus x squared at, I guess, fixed x. Oh, no, now I'm confusing myself again because they're integrating over x instead of over y. Yeah, I should have read this example more carefully. So let's see. So we're integrating over x's dx from minus r to r. And at each value of x, I guess, by symmetry, I guess it's just half of this. So this would be x times the y value, which is root r squared minus x squared. Why is it squaring? Let's see. Do you see, perhaps this will turn into a challenge because I did not read the example before doing it. So do you see why in this integral we're doing this integral of r squared minus x squared whole thing squared rather than just the integral of y, which would be the square root of this?
Nope, since I hardly understand the y center of mass equation itself.
Okay. Well, let's see. So if we integrate over x's, at each x, we're trying to find, I guess, the y. Oh, I see what it is. Okay. So at each of these x's, we want the y times the length of it. I see. Okay, I'm confused. They did this integral in a weird way. I would have done, if I were finding this problem, I would have integrated dy, so you would have these horizontal slices, because all of these are at a fixed y. They are integrating over x, which means they do something different. So here is what they're doing. I should draw a better picture. Here's what they're doing in this example to find the center of mass, this y center of mass equation. So the dividing by the area downstairs is clear, because that's the total mass if this thing has density 1. So you could ask the question, how can I add up all of the contributions from different y's, but integrate over x? And the way to do that is as follows. If you're at a fixed x, and you would like to add up all of the contributions to the y center of mass from guys that are at that fixed x, by guys I mean points, all of the points at that fixed x lie on a vertical line like this. So you could ask, what are all of the contributions to the y center of mass from these guys? Well, y center of mass is supposed to be basically the integral of, y times the constant density sigma, which is supposed to be 1 dy or something. So, or I guess this is times a small area because sigma is mass per unit area. So this is supposed to be times a tiny area. So how do we get a tiny area and then multiply by all the y values on that area? Well, we get a small area by saying, well, we're going to look at a little chunk from x to x plus delta x, or x plus dx, and then you just ask, okay, how do I add up all of the y values for guys in this little chunk? Well, for each of those y values, we're going to have, some y being root r squared minus x squared by this equation, which is from Pythagoras. So this is the y of one guy along one slice of this vertical strip. And then you say, well, there's not just one guy along this vertical strip, there's many different guys going from 0 up to this top y, this this fixed y at the top for a given x. So in order to integrate up all of those contributions, what I should really be doing is integrating from 0 up to this total y. So integrating along these vertical slices, the horizontal slices, integrate all of those contributions, which looks like basically y dy. That's what's going to give us a 1/2, maybe I should use a different y, y top. So this is 1/2 y top quantity squared, is the total contributions from all of the y's at this fixed x, right? So kind of botched that explanation, but let me just say it one more time. We're going to integrate over x instead of over y. For each fixed x, I'm going to add up all of the contributions to the y center of mass. To add up all of the y contributions, I integrate up along a vertical strip. What do I integrate up? I should be integrating y for each slice along this strip. So I'm integrating all of the y's from 0 to the top, but what is the top at a fixed x? It's basically root r squared minus x squared dy. So for each of these strips, I really end up with a 1/2 times y squared, or a 1/2 times r squared minus x squared. Okay, so we're breaking this guy up into strips. That's the point. And then that integral runs over all the x's. So for each x, you have a strip, and this is what the strip does. Okay, that's better, I think, or at least for me it feels better. So anyway, so here's the 1/2 from the y squared and then the y squared. But the y is root r squared minus x squared. There's a half outside. We're integrating from minus r to r, but by symmetry that's the same as just doing twice the integral from 0 to r. So we do twice the integral from 0 to r. That 2 kills this 1/2. This 1/2 downstairs turns into a 2 upstairs. So it's 2 over pi r squared times the integral from 0 to r squared, or 0 to r of r squared minus x squared. And then we just evaluate those two integrals dx. So the first one's an r squared x, the second one's a minus 1/3 x cubed. Plug in 0, plug in r. The r1 gives you an r cubed minus r cubed over 3, which gives us a 2r cubed over 3. So the final answer is this thing, this 4r over 3 pi. Okay, and visually it makes sense, since the center of mass is, kind of somehow, on this vertical axis at 4r over 3 pi is somehow it kind of prefers the larger amount of y mass, which is near the base of the semicircle, less so than towards the top. Good. Okay, I apologize for botching the stuff about the strips, but maybe I'll have a challenge that goes through another example like this in more detail. But integrating all of the y's on a strip is kind of a tricky thing. Thoughts on this stuff?
I do not believe I understand this well enough to replicate it.
Okay. Yeah, maybe I should look for another example and post it in a challenge. But yeah, when I saw this one in the textbook, I thought, oh, this looks very easy. I should be able to figure it out on the fly, but I forgot about this strip trick.
Context.
Yes, strip trick is different from the stripper trick. That's a very different trick. Okay, so now let's back up a bit and ask the question, where would this idea of center of mass arise physically? So why is this interesting? Okay, the reason is as follows. If you have some complicated shape, some object which is made up of many particles or something like that, and you would like to simplify the study of some forces acting on that object, the center of mass is your friend, because you can simplify the problem by simply adding up all of the total forces acting on different parts of it, so you find the net force, and interpret that as the force on a point particle located at the center of mass. So let me explain why that's true. We'll just start with Newton's law summed over all of the particles in a system. So you could think of this as, a bunch of different atoms making up this box or something. So each of those atoms satisfies F equals ma, or I guess there should really be a with an arrow over it because we're doing vectors. But anyway, the sum of the F's is the sum of the ma's. The definition of acceleration is the second derivative of position with respect to time. So this is the sum of the m's times the d squared x's by dt squareds. Derivative is linear, so the derivative or second derivative of a sum times some numbers is the same as the sum of those numbers times the second derivatives. So we can pull out the second derivative overall and let that thing act on the sum of the masses times the positions. But now this thing in parentheses is that center of mass object that we just defined a moment ago. So this thing in parentheses is exactly the center of mass vector x center of mass. Right, because the sum of the masses times the positions may be up to some factor of the total mass that we ignored. So I guess I should put that total mass back in at the bottom. So this, yeah, so there should have been a total mass. You would normally divide by the total mass. So this thing is actually the center of mass multiplied by the total mass. So that means that you can interpret the sum of all of the forces as the acceleration of a point particle whose total mass is the sum of all of the masses in your system. So why is this useful? If you have some system that's going to do some complicated motion, like for instance, you take a box like this and you tilt it on, about one axis or something, and ask how far do you have to tilt it before it starts to fall over, right? Well, naively, this seems pretty complicated because you have gravity acting on all of these different parts of the box separately. So when this thing actually falls, you're going to have some complicated motion where it's tumbling as it falls, so there's some rotational motion, which might be complicated to explain. But if you just want to understand the center of mass motion, you could say, well, that part's very simple because I just pick a point at the center of mass and say that point at the center of mass is just moving or has some force pointing downwards, where the magnitude of that force is the total mass m times gravity g. And if that downward force due to gravity can be countered by some force from the floor, some normal force or something, then this thing might stay upright. But when I tilt it too far over so that this center of mass is now kind of hanging over the floor rather than pointing downwards into the body, then this downward force on the center of mass overcomes the normal force. And then the center of mass just moves straight down, the same way a point particle would move straight down when you dropped it. So even though the whole thing is doing something complicated, some rotating, the center of mass is moving straight down under gravity. Very nice. Useful thing to do to simplify rotational analysis. But okay, good. Thoughts on this?
I do not have any thoughts on that.
Okay. When did we start? So I know 5:30. So I'm an hour and 10 minutes in, basically. Although we fucked about a little bit at the beginning with other stuff. But okay, so let's do the third one. So we've done density. Just integrate, some density function to get the total mass. Center of mass was integrate the position times the density. You could say, what happens if you go up higher? What if you integrate not x times the density, but x squared times the density? Does that give you something useful? And the answer is yes. But first I want to tell you why it's useful. So again, assume you have some random shaped object, so some blob, which is again built out of many masses m sub I. And the whole blob is spinning with some angular velocity which we measure in radians per second, for reasons which you'll see shortly. So the whole thing is spinning about this axis with some number omega radians per second. And you want to know what is the total energy of this system due to the motion that is due to all of this rotation, all of this rotary motion. That sounds like a hard problem. But it's actually not so hard if you just break it up into chunks and find the energy of each chunk. So let's look a little more closely at this thing. So we're going to break this thing into tiny chunks. So here's a little chunk which has some mass, maybe m sub I. So the energy of this particle I, well, we know the kinetic energy of this guy, it's supposed to be a half m sub I v sub I squared. So we just have to understand how fast, what is the speed v sub I of this little chunk. Well, that's not so hard either, because this guy is going in a circle around this axis of rotation. This guy's going in a circle about this central, maybe z-axis or something here. So to find how fast it is, its velocity v, there's a pretty simple trick. I mean, you could prove this using more general methods in physics, but we want to know basically what is the velocity, which would be the distance divided by the time it takes to go that distance. Well, if this guy is at some radius lowercase r from the central axis, and he's going in a circle about that axis, you can see, since he's kind of moving in a uniform circular motion, that his speed is always pointing along the circle, right? He's always pointing directly along the circle. So to find his velocity, we can just say, well, the distance that he travels when he goes all the way around the circle is just 2 pi r, the circumference. And we want to divide by the amount of time that it takes him to go around the circle. So my question to you, if he's going omega radians per second, how long does it take him to go all the way around the circle? Which is all 2 pi radians, I guess.
I am thinking, oh god, what is the name of the letter?
Omega.
I believe omega inverse.
Not omega inverse, so let's think about it. So omega is radians per second. So it's omega times the time equals 2 pi, right? We're asking what time is needed to go 2 pi radians, which are all the way around the circle. So the answer is not omega inverse, but 2 pi over omega, right? Because he has to go 2 pi radians to go all the way around. So,
Okay, I was assuming that omega was speed and not, well, I think.
Yeah, you were thinking
Okay,
cycles per second. You were thinking hertz, right? You were thinking how many times does it go around per revolutions per second is the word you were thinking, right? Omega's not in revolutions per second, it's in radians per second. If it were revolutions per second, the time would be 1 over omega. I agree. But does this make sense, this picture that you need omega times the time we want has to be 2 pi to go all the way around a circle, so t is 2 pi over omega.
I do not believe it is clear. Let me think about it. So angular velocity times, is that any time?
That's the time. We're trying to solve for the time that it takes to go all the way around the circle. So this is the time we want, right?
Okay.
So we're setting up an equation. The time that we want is the time it takes to go 2 pi radians. So you just say, if I go omega radians in 1 second, and I multiply that by some number of seconds, and I want that product to be 2 pi, then what is the time in seconds I need? And the answer is just that I need that time to be 2 pi over omega, right?
Okay. This is clear.
Good, good. Yeah, it's just like regular velocity. Like if this guy's going 10 radians per second, and you ask how long does it take to go 2 pi radians, it's 2 pi over 10, right? Okay, so this in the bottom is 2 pi divided by omega. And now you see why it's nice to use radians per second instead of revolutions per second, because the 2 pi's cancel. Right, so these 2 pi's go away, and this 1 over omega downstairs turns into an omega upstairs. So the answer is basically just r times omega. So this is something worth memorizing if you take physics. For an object moving in a circle, going at omega radians per second, its velocity, meters per second, is just the radius in meters times omega in radians per second. Right, so the units work out. The left side is meters per second, the right side is meters times radians per second, and we know radians are dimensionless, right? Radians.
Okay, yeah, I was about to say.
Crucial.
We can do this because radians are dimensionless, right?
That's exactly what
Unlike degrees. Okay.
Yes, it's very important, right? And just to beat a dead horse, the reason why radians are dimensionless is because an angle in radians is divided by this arc length s divided by the radius r. So if the arc length is in meters and the radius is in meters, the angle in radians is meters over meters, which has no units. Right? Very important. Okay, so
I am going to grab a drink real quick, like 30 seconds.
I'll be here.
But could you identify the drink by the noise?
I didn't hear a noise, but I'm going to assume it's Coke Zero.
Yeah.
Lol. Okay, so let's recap. For an object going in a circle of radius r with angular velocity omega, its speed in meters per second is r times omega. That's just an important universal result, which will come up over and over if you take physics. So why did we do that? Because we want to find the energy of this particle, so we had to know v, and now we know v is r omega. So the energy of this particle is now 1/2 times m sub I, the mass of that particle, times v sub I, which I'll write that as r sub I omega quantity squared. Now notice I did not put an index I on omega, because all of the particles are moving with the same angular velocity omega. Right? Omega is a constant over all particles I. So I don't put a subscript. It's always the same. That's actually important. So anyway, the energy of this ith particle is just 1/2 mi/ri squared omega squared. Okay, so that's our intermediate result. We're trying to find the total energy of this object by adding up the energies of all of the little chunks. And now we know each chunk has energy E sub I is 1/2 m sub I r sub I squared omega squared. So now all that remains is to add them up. Let me zoom out so you can see what the sum looks like when you add them up. Okay, so below I've simply copied what I just explained to you. These guys are moving in circles with V as our omega, so the energy is 1/2 sum. Now this is the total energy, E total. So the total energy is the sum from I equals 1 to n of 1/2 m sub I v sub I squared, which as we just saw is 1/2 m sub I r sub I squared omega squared. And now here's where the magic happens. Because that omega is a constant, you can pull it out of the sum. Right, we had an omega squared inside the sum, and I'm going to pull it out of the sum. So what did we just do? We wrote the total energy, the sum of the energies of all of the particles, as a product of two things. One of the things is just geometry. By geometry, I mean, to do this sum, all you have to know is where the particles are, what their masses are, and how far away they are from the central axis. So knowing where all the pieces of your shape are and how far they are away from the axis is really just telling you basically the shape. So this number in the middle is just a constant which only depends on the geometry or shape of the rotating object. This thing over here, omega, is the dynamics, right? Omega is just telling you how fast the thing is rotating. So omega knows nothing about the shape. You could have a sphere rotating with a certain angular velocity omega, or a cylinder, or a rod. It doesn't matter. Omega is just a speed that just tells you about the dynamics. So we've split the energy into a constant, which knows about the geometry, and a different constant, which knows about the dynamics. So whenever you've made such a split, it makes sense to define a new letter for the term in the middle, which now is written as an ugly sum, and that's called the letter I, which is the moment of inertia. Moment of inertia. So you may have seen this before in the context of angular momentum, where there you would write, I guess, L is I omega. So you can also write this for vectors, L is I omega. But I chose to motivate it with the total energy. So now what we know is the energy of a body rotating with angular velocity omega is 1/2 I omega squared. Now I find this equation just sort of deeply satisfying, because the parallel with the energy of a particle being 1/2 mv squared is very close, right? It looks exactly the same, except now for this rotational motion, there's just an effective mass I, which is the sum of all these mr squareds, because this is an effective mass for rotational motion, I omega squared. Okay, so last step for moment of inertia is, what about the continuous case? Well, you've already seen this like 3 times now, so I'm not going to belabor the point, but if you have a continuous mass distribution, you just take the limit as those little chunks m sub I become very small. The sum turns into an integral. So the moment of inertia for a continuous body is the integral of all of the r squareds, where r is the distance from the central rotary axis, r squared times dm. And again, you usually like to write the mass of a little chunk m not as dm, but in terms of the density. So for instance, if this were a 3-dimensional integral, you could write the mass of a little chunk m as the density times a little volume, dx, dy, dz. So this is the 3-dimensional version. I've already said this a couple times now, but just to distinguish, sometimes you have a linear density, which would be in like grams or kilograms per meter. You can also have an area density, which is grams or kilograms per meter squared. Here I've written this as a volume density, so this would be grams per meter cubed. And there's, the similar version of this equation in those other 2 cases is pretty obvious. I mean, if you have I for some linear thing like a rod, it would just be basically r squared times the linear density dx. If it were I for some plate, some 2-dimensional thing, you would have integral of r squared times sigma, maybe dx dy or something, a little area. They all carry through. But the point I want you to remember is that the moment of inertia looks kind of similar to the center of mass, which was the sum of the mx's, but now the position is squared, right? So it's the sum of the mr squareds, or the integral of the r squareds times the density, if you like. Okay, I find this very sexy, but I don't know. Thoughts or comments on this? muted again. Oh no, what is this? Not muted. It stopped working. Well, apparently you can hear me since you said not muted. So what stopped working? Maybe that means your microphone stopped working or something.
Work? Come on.
I heard something.
Does that work?
Yeah, now I hear things. Okay, that was weird, but...
Now I'm using my laptop microphone. Let me see if the headset works now.
Okay.
Work. I'll just use the desktop mic and figure this out later.
Okay, sounds good. Thoughts on moment of inertia?
I do not have any thoughts.
Okay. Good. So I think I have a challenge that will make this... Yeah, I love this. So I first saw this problem when I was in high school, and it's a very simple question, but for some reason I was just totally enamored by this setup. So let me just tell you what the setup is. We're going to have a race between a few different shapes. And by race, I mean we're going to start at the top of a ramp by putting each of these shapes in the same position. We're going to hold them all in place, and then we're going to let go at the same time and see which shape reaches the bottom first. Now, importantly, all of these shapes have the same mass, so they all have the same mass, lowercase m, and they all have the same radius, although I should be clear, by radius I mean the distance from the center of the object, or where it's going to rotate as it rolls down the ramp, to the edge of the object. So this radius is r for this hollow sphere. This, for the yellow one, is a solid filled-in sphere, has a radius r. This thing is like a little hoop, like a hula hoop, and the radius from the center to the edge of the hula hoop is still r. And this guy here is a filled-in hollow cylinder like a drum or something. So this is like rolling a drum of radius r. So anyway, they all have the same mass and the same radius, but they have different moments of inertia, because if you add up the mr squareds, or integrate the r squareds, over the whole geometry, even though their radius is the same, as you can see, the locations of the masses are different, right? Like for instance, in the hula hoop, all of the mass is at the rim, but for the solid filled-in cylinder, the mass is evenly distributed from the center to the rim. So since the mass distribution is different, the moment of inertia, will be different. So let me just set up the problem, and then I'll ask you to kind of walk me through your reasoning. This is more of just a thinking question, not a math question. But here's what's going to happen. These guys start with some potential energy, which is basically mgh, for the initial height. So the potential energy is going to be converted into kinetic energy for each of them. But the kinetic energy for an object which is both moving and rotating is a sum of two terms. It's a 1/2 mv squared for the translational motion, the moving down the ramp, and then it's a sum of a second term, a 1/2 I omega squared for the rotating. So all of these guys are going to convert potential energy, the same amount of potential energy, because they start from the same place. They're all going to convert that potential energy into kinetic energy, but for these guys, the split of kinetic energy into translation and rotation will be different, because some of these guys have bigger eyes. So the guys with the bigger eyes are going to have more of the energy going into the second term, right? Because I is larger. Okay, so let me just ask you what you think. Suppose I tell you, which is true, the following. I tell you the moment of inertia I for the ring, or the hula hoop, is the biggest. Next is the spherical shell, the red guy, the hollow sphere at the right. Next, largest moment of inertia is the filled-in cylinder or drum. And the smallest moment of inertia is the yellow solid sphere. So if I tell you that this is the order in descending order of moment of inertia, what order do you think these guys will reach the bottom? Who gets there first, second, third, and fourth?
Okay, so I mostly say this because I've seen a similar but not the same problem before, comparing specifically a sphere and a shell. But I believe that the sphere is going to reach the bottom quickest because it takes the least torque to accelerate, and thus gravity can pull it down the quickest, just based off of how the moment of inertia is focused more towards the quote-unquote center.
Yeah, true. So can you explain why that's true from the energy conservation perspective?
Let's see. Can I? Probably not. Can I try? Probably not.
Well, I mean, that's what we're learning today, so you should try to explain it using that technology.
Let's see.
But yeah, you're right. The sphere wins, and the sphere has the smallest moment of inertia. So why does the sphere move faster than the shell if the sphere has the smaller moment of inertia?
Let's see. Since the moment of inertia is smaller, the entire 1/2 L angular 1/2 L
I.
angular velocity squared. I mean, yeah, that entire term is smaller. Let's see. Oh,
Yeah. So if this term is,
I think so. It seems that the okay is 1/2 mv squared the same for all of these.
no, that's the point. They have
Okay.
different speeds, right? The one that has the bigger speed reaches the bottom first, right? So this equation is different
Let's
for each
see.
of these guys.
I'm rolling my fingers on my laptop and then realizing that it's making the mic go off.
Okay, well let's just think about the sphere in the shell. So the sphere in the shell starts.
Are you being impatient?
Well, okay. Are you still thinking about it?
I'm thinking, but I'm not making progress.
Yeah. Okay. Well, let's just think. So the sphere and the shell start with the same potential energy. They convert the potential energy into kinetic energy differently. Why differently? Because the sphere has a small moment of inertia I. So if you start with a budget of potential energy, and you can either spend that budget on motion, how fast you're going, or how much you're rotating, but I is small, that means you're going to spend a small amount of your budget on how fast you're rotating, and a large amount of your budget on how fast you're moving, right? So the one with the smaller moment of inertia is spending less of its energy on the second term and more of its energy on the first term, which means the velocity is faster, so it's going faster.
Yes, I was about to. What I was going to say is that more gravitational energy is being put into the movement than the rotation. Yeah.
Yeah, that's exactly right. Yeah. So, yeah, that's the case for the sphere, and then in the case of the ring, it's entirely the opposite. The ring has a giant moment of inertia, so it's spending all of its energy on rotating and not spending very much of its energy on moving fast. So this guy is moving slowly, which means he reaches the bottom last, right? So, good, this is the answer. Yeah, if you roll objects down an incline, the ones with smaller moments of inertia are going to reach the bottom first, because they're spending less of their energy on rotation and more of it on moving fast. Good. Okay, we can actually make that precise. So I'll just.
You see, this would have won like first place in the 4th grade science fair.
What, rolling things down an incline?
Yeah, specifically for different things like this.
Yeah, I mean, it's a cute experiment, right? It's a classic demo in freshman physics. They always do this demo in lectures, but. Okay, well, I was just saying that in a very hand-waving... I just said words at you. I didn't do any math. So let me just convince you that we could make that intuition I just gave you precise. I'll just do it for one case, like the sphere. So if the sphere, for instance, is rolling without slipping, that means that all of the objects are rotating about some central axis with the same angular velocity omega, and by basically the same argument I showed you a couple slides ago, that means we have v equals r omega for the center of mass velocity of this guy. So if we just write conservation of energy, here's the gravitational potential energy, here's the linear kinetic energy, Ke linear, Here's the rotary kinetic energy, Ke rotary. The rotary is a half I omega squared, but I solved this equation for omega to get omega's V over R. And I put in the V over R for omega. And then I just solved this equation for V to see how fast it's going. How do I solve this for V? Well, I have mgh is 1/2 mv squared plus 1/2 I over R squared from the R squared downstairs times V squared. I just factor out the V squared and then divide by all this chunk and take a square root. So at the first step I have V squared, I guess I can multiply by 2 to get rid of these fractions. So 2 mgh over, well, what's this? M, what's this guy? M plus I over R squared. So this is V squared. And now we just see very explicitly that the guys with bigger I's are going to go slower, right? Because I appears in the denominator. So if I is huge, the denominator gets bigger and the object moves more slowly. But if I is small, the denominator gets smaller and the guy goes faster. Okay, so now you can just see what the answer is. You could compute, and I'll give you this in some DCs, the moment of inertia for a sphere is 2/5 mr squared. For a cylinder, it's 1/2 mr squared. For the shell, it's 2/3 mr squared. And for the ring, it's mr squared. So this is in the direction of increasing moment of inertia, which means slower. So the speed, or the speeds go in the other way, so the order in which they finish will be sphere first, then cylinder, then shell, then a ring. Okay. So you can actually just see the simulation where people show you how fast these things are moving at each point in time just by solving the equations of motion for these guys. And here's what it looks like basically. So they roll down, and as we expect, the sphere hits first, and then the shell hits last because he has the giant jet of inertia. So the green guy is there last. So I think it should be yellow, blue, red, green. Yeah. Good. Exactly as we expected. So there's one other simulation I like. This one's on Reddit. So this one, in addition to those 4 guys, it also has this like cube. Now the cube is actually just skidding. It's pure sliding without rolling. So the cube actually beats all of the other guys, because in the cube case, he's not even rotating. So all of his energy is going into just pure speed, and none of it is going into I. So you could think of that as like the I equals 0.
That's such a hacky way to win.
Yeah, it's just just cheat a little bit. This is ignoring friction, by the way, but it's still cute. Okay, good. I like that rather a lot. So kind of fun. Okay, I have 1 act left, and I guess I should quit in about 20 minutes or so. So we'll see how much of this we get through, because there's some challenges. But any questions on moment of inertia or the rolling racer problem or whatever?
There's some challenges. Eyes widen.
Yeah, we might not get through.
I do not have any thoughts, comments, questions, or concerns before we go into the next act.
Okay, let's try this then. So I want to tell you a bit more about gas physics. So last time we used integrals basically to get the ideal gas law, but I claim that there's a lot more that we can do with integration in thermodynamics and gas physics and gas chemistry. So one question you could ask is the following. The ideal gas law totally ignores the effects of gravity, right? The ideal gas law just assumes you have particles in a box that feel no gravitational force, which is, maybe a good approximation if, the total size of the gas is small or something, or gravity is weak. But let's try to solve the problem of how a gas behaves, how its pressure behaves, in a slightly different case where we take gravity into account. So, okay, I'll set up the problem for you. Suppose you have this column of a gas. So this is like, you can think of this as like a column of air in the atmosphere or something. Like this is all of the air above Earth, and we're just going to consider this little like cube part. Restrict our attention to this column. So we're going to include the effects of gravity, and we're basically going to write just Newton's second law again, F equals ma, for the gas which is contained within a little slice. So the gas which is in this little rectangular prism here. And we're also going to assume that the gas is in equilibrium, which means it's not moving, it's not accelerating. So the gas is just kind of, the gas particles are bumping around randomly, but they're not, they're not all moving upwards or all moving downwards. So F equals ma equals 0 because it's not accelerating in either direction. So now we just have to ask, what are the forces that act on this blue section, you know, the gas which is contained in this little prism? Well, I claim there's three forces. So there's the gravitational force, so F gravitational force, pointing downward. Now we know the gravitational force is roughly minus mg, but we have to know what the mass is. What is the mass of the gas in here? Well, the mass is going to be the density times the volume. So let me write that first for you.
You're lagging bad.
Oh no. Yeah, I guess I'm on red. Well, I can wait a second and see if that gets better.
It's taking a fair bit. Usually you tab over and it's suddenly better.
Yeah, it's probably my roommates are watching Netflix or something. Ah, now it's green. Is that better?
Yes.
Okay. Good. Okay, back to gases. Okay, so let's write the three forces. The first one is the gravitational force, which I claim has a minus sign. And then the mass of this gas. What is the mass? Well, the mass is the density, which I'll write with the Greek letter rho, times the volume. Right? We're going to assume constant density, so there's no integrals we have to do. What is the volume? Well, if this guy has cross-sectional area A, and we're looking at this little prism with height dh, then the volume is A dh. So the total mass, therefore, oh sorry, I forgot a g. Right? It's supposed to be mg. So anyway, the gravitational force is minus rho A dh g. Okay, so that's the gravitational force. But there's also pressure, right? There's pressure, which is a force per unit area. And there is two separate pressure forces acting on this prism at the two shaded areas. So why is that? Well, simply because this chunk of gas with height dh is getting pushed up upon by all of the gas below it, right? So the gas below it has some pressure P, which is pushing up on this guy. The gas above it is pushing down with some different pressure. We're assuming the pressure is changing, right? So this guy feels some push from the guys below him and some push from the guys above him. And the guy, well, to emphasize that they could be different, we're going to write pressure at the evaluated at the height h plus dh for the guys pushing down on him. That's this one. And then we're going to write pressure evaluated at the height h for the guys pushing up on him. Right, so we're trying to make pressure a function of height, basically. So I claim F pressure is supposed to be a sum of two terms. Now remember, pressure is force per unit area. So to get the force, we have to multiply the pressure by an area. So F pressure is supposed to be a positive pressure at h times A, and a negative pressure at the higher point, h plus dh, times A. Okay, so now we have our equation. The total force is 0, which means we're supposed to have, let's see, minus rho A G dh, which is the first guy, plus P of H A, minus P of H plus dh, A equals 0. So that's just force balance. This is Newton's second law. We're just saying add up all the forces on this guy. It should be 0 because the gas is not accelerating. And there's three forces: gravity pulling it downwards, gas below it pushes up, gas above it pushes down. Okay, questions on that stuff?
No, this is clear.
Okay. Well, now you're going to see something cute, or maybe I thought it was cute the first time I saw this, but as you go on in chemistry and physical sciences, you'll see that all the time people write down equations like this and then take a limit as h goes to 0, or as some variable more generally goes to 0, in order to get a derivative. And you could probably see exactly what's going to happen, because we have P of H plus dH, a P of H, and a dH. So you can probably see how I'm going to massage this to make it look like a derivative. And that's exactly what I'm going to do on the next slide. So here's what happens. Again, by Newton's second law, here's what I wrote a moment ago. Here's the gravitational force, the pressure pushing up, the pressure pushing down. Now I'm just going to rearrange this equation by moving the negative gravity force to the right side and then dividing by dH. So when I move this guy to the right and divide by dH, notice I can also cancel the area, because area appears in all of these. Actually, no, not move this guy to the right. I'm going to move the pressures to the right. So I move these guys over, which means I add P of H plus dH and subtract P of H. So when I do that, on the left side, I have minus rho G. I'm going to divide by dH. On the right side, I have P at H plus dH minus P at H all over dH. And now this probably looks suspiciously familiar as the definition of a derivative. So now, I guess dH. So I have massaged this to make it look like the right-hand side is a derivative, and indeed, if you take the limit as dH goes to 0, the right side turns, or I guess the left as I've written it here, that thing turns into exactly the derivative of the pressure function with respect to height, h. So just by using Newton's law, we found an equation that tells you about the derivative of pressure with respect to height, and it relates it to the density. So we'd like to use integrals to solve this, right? We would like to just integrate both sides over h, and then we would have our answer for what is the pressure as a function of height. But there's a problem. And the problem is that this density rho is actually not constant either. The density is going to change with height. Density is a function of height, which is maybe intuitively obvious. If you have a column of air, you would think near the top it would be less dense, because gravity pulls it down, so it should be more dense at the bottom, because gas particles pile up at the bottom. But how do you do that? I mean, how do you precisely write down the equation that tells you how much bunching happens? So how do you write down the density as a function of pressure? Well, I will ask you that as a challenge. It's basically just the ideal gas law. So here's the challenge. Suppose you have, again, an ideal gas, which n particles, a total volume v, and all of the particles have equal mass m. So by definition of density, density is mass over volume, here total mass over total volume. The total mass is the number of particles times the mass of each particle, so n times m. The total volume is just v. And now I will ask you, if I want to eliminate v to write the density as a function of pressure using the ideal gas law, what should I do?
nRT over v over p equals v. Okay.
Okay, so you say
yeah.
nRT.
V equals nRT, thus v equals nRT over p.
Okay, so then when I plug that in, what is the density?
Thus, we have nm over, well, nmp over nRT.
For nRT, good.
And I see that n's are going to cancel,
Yeah, so
I believe.
So I think it's just mp over RT. Yeah.
Yeah.
Good, okay. Very nice. So, yeah, you have used here the chemist notation of using R instead of the Boltzmann constant, which I used on the next slide, but this is totally fine. This is correct in some different conventions. So, good. Let's see that again.
So, where R equals KB, yeah.
Yeah, yeah. So, so your answer is fine, but if you just do this, I mean, if you replace KB with R in my answer, it's exactly the same. So you just use PV as NKBT. Then N's cancel top and bottom. The P goes upstairs, so it's PM over either RT or KBT. Good. Okay, so that's nice. Now another challenge for you. Before, on the first part of this section, we got this equation. Derivative of P is minus rho G. Then you just told me rho is PM over KBT, or RT. Now I'll ask you, combine those two equations, move all of the P's and dPdH's to the left-hand side, so get an equation where those are on the left-hand side and the right side is just constants, and then integrate both sides with respect to h, from 0 to capital H, to get the answer. And as usual, when you integrate, you have to know what the thing is doing at the bottom endpoint, so you're allowed to assume that the pressure at height 0 is this number P0. So that will show up somewhere. But anyway, I'll let you do it. So what should I write to solve this?
All right, we see that dP over, well, dPdH equals negative thing G.
Where things.
What is thing? Well, I'm referring to the weird P.
Yeah, it's rho. It's just the
Rho. Could not remember. Okay, so dp over dh equals negative rho g, thus negative dp dh times 1 over g equals rho.
So you say minus dp dh over g equals rho. Okay, and we want to plug in for rho in terms of p, right? So what is that?
Yes. So thing on the left is equal to pm over kbt, and we want to move the p to the left side somehow, so let's multiply each side by 1 over p.
Okay, so we multiply by 1 over p. The left side has a 1 over p now, and I want to get constants on the right. So now
Let's multiply each side by g.
okay, so got this g. Okay, looks good. So now the left side has p and dpdh, and the right side has all constants. So we want to integrate now. Right. So now what happens? This will just be a simple u sub, actually totally obvious u sub. If I integrate both sides dh from 0 to capital H, now what do I get?
All right. So the left side is equal to, let's see, remember. Well, the right side is equal to h gm over kbt.
Yeah, that's easy. So capital H gm over kbt. Good.
Cough, cough. And the right side you said was a u sub? Just trying to, it should be exceedingly obvious, you say.
Yeah, I mean this should, I mean, you could either use the mnemonic. Remember how u sub works. The mnemonic is that, you know, you can somehow pretend these are fractions and cancel the h's or something and instead integrate dp. But if you don't like that mnemonic, then on the left side you should just make the u sub u equals p, then du is
equals dp d,
well,
yeah.
It's dp dh dh.
Well, dp, yeah.
Right.
Okay.
So this whole thing is du.
Is
this is 1 over u with a minus sign, right?
So negative log h.
Yeah, so negative log. Well, be careful because the endpoints change. Yeah. So.
Oh right.
So this is, well, I'll put the big boys in and then you can tell me. So how do the bounds change when we go from h to p? So when h is 0, what is p? And when h is capital H, what is p? Oops.
Based off of the u equals p formula, nothing changed, unless I'm confused.
No, something definitely changed, right? So, I mean, here I gave you the variable substitutions, but whenever you change variables, the old endpoints tell you this means the variable's h here. So this means h equals 0 in the old integral, and h equals capital H in the new integral, or in the old integral at the top. Now we're changing variables to pressure. So you have to ask, what is pressure when height is 0? Well, I told you that. I told you that in the problem statement. When height is 0, the pressure is P0. So the new lower endpoint is P0. Then you ask, what is pressure when height is capital H? Well, that's the thing we're trying to solve for. So that's just pressure, the pressure function evaluated at capital H, right? So.
Yes.
Okay. All right, so we're almost done. So I'll plug in these guys and solve this. I'll copy the right-hand side here. Solve this and tell me what we get. Actually, I'm going to put the minus on the right because I like that better. But anyway, go on.
So we have log of pH over P equals negative HGM over KBT, where I simplified using log rules.
Good. So log P of H, I should have called that P0, sorry.
Well, yeah, P0, apologies.
No, that's my fault. I wrote the wrong thing. Good. Okay, so log of pH over P0, we want to solve for P of H, so what do I do to both sides?
We place each side to the, we exp each side, there we go.
Yeah, exponentiate both sides. So on the left side, that kills the log. I'm going to write this kind of shitty equation now where there's a big gap because I'm too lazy, but now the right side has a big old exponential, and I guess I should, what, multiply by P0 or something?
Yeah.
So P of H is P0 e to the disjunct. That's the answer. Now this is a pretty famous formula in atmospheric chemistry and physical chemistry called the barometric formula. So let's just think about what this says. This is...
Amazingly, Hg is in the formula.
Yeah, well, this is not mercury. This is the product.
Yeah, I know.
Good. Yeah, you don't want. My mom always tells me stories of in high school chemistry. They actually had mercury, and when the teacher left the room to do a smoke break, kids would pour mercury into their hands and throw it over across the room and play with it. And whenever she tells me that story, I'm like, probably all those people
Oh
have
my
cancer now.
God. If they are still alive.
Back in the good old days where teachers left in the middle of the class to take a fucking smoke break.
I remember hearing stories about the asbestos in the ceilings and getting pencils stuck in them.
Yeah, that's yeah. The old times sound like they were fun, but good.
Fun and cancerous.
Yeah. So what is
Literally.
this? What does this tell us? So this is a modification of the ideal gas law that tells you not only how pressure, well, we've killed volume basically because we assume volume is fixed for our cylinder, but this now tells us how pressure depends on height. So let's just graph it. What it looks like is that, there's some pressure P0, which is at basically sea level at height 0. And then as you increase in height, the pressure is supposed to kind of fall off exponentially, where the speed of that fall off is controlled by G and the mass of the gas and the temperature. So a higher mass means this thing falls off faster. So the intuition makes sense, right?
Oh, that is cool.
Yeah, it makes a lot of sense.
So dense atmospheres have they fall off quick. Okay.
Yeah. So if you have something like the surface of Venus, where there's a lot of very heavy gases in the atmosphere, although the pressure at sea level at the ground is very high, the atmosphere thins out very quickly as you go up because the gas is heavy, right? So intuitively, if the gas is heavy, it just costs a lot of energy for that gas to go high in the atmosphere, which means it doesn't, right? It just kind of stays close to the surface and it falls off and thins out very quickly as you go up. Good.
I'm curious what mass you would need for it to fall off to 0.1%, 1 meter above the surface.
Oh, well, I mean, you could just plug numbers into this equation and solve for that, because we know what all these numbers are. You probably need something really heavy, like, I don't know, probably sulfur hexafluoride is not heavy enough. It also depends on the temperature. I guess you're assuming STP or something, or room temperature, 273 or whatever. But
so like ST. Because pressure
yeah, P is changing.
Would be a bit ludicrous.
Yeah, the pressure is changing, so I shouldn't say the P in STP. It's not 1 atmosphere, but okay, good. So just to review what we did. We got this equation for dPdH from Newton's law. We plugged in the ideal gas law on the right, and then this gave us some equation with P's on the left and constants on the right. Took an integral, integrate on the left, do a U sub, or just cancel these if you prefer, to integrate 1 over P. Integral of 1 over P is a log. This is wrong. This should be, I forgot to change the bounds from P0 to P of H. On the right side, it's just some number. And as you said, you exponentiate both sides. And this is the barometric formula. So I will comment that this formula is a very coarse approximation. So we made a lot of simplifying assumptions. The most obviously wrong assumption is we assumed the temperature was constant, right? So we assumed the temperature everywhere in this column of gas is the same number, which is pretty obviously not true in any reasonable atmosphere. As you go upwards in a realistic atmosphere, the temperature is decreasing as well.
Well, it's not realistic, but it can be attained in a lab.
Yeah. I mean, this is, as we say in science, this approximation is valid in a particular regime, where by regime we mean you could prepare an experiment in lab where the temperature is indeed forced to be approximately constant, and then you could test how well this equation does. And in such a scenario where the temperature is close to constant, and where the ideal gas law is a good approximation, which is just the statement that, the particles aren't interacting that much, they're fairly dilute and whatever, then yeah, in that regime, this thing will be a very good approximation.
But that's not a common occurrence, so it's not it's not as useful as it could be.
Yeah, it's not obviously as useful for studying the Earth's atmosphere, where the temperature obviously gets colder as you go up. So, I mean, you could modify this.
And then hotter, and then colder.
Yeah, I guess you have some ionosphere shit or something, but yeah, well, it's hard to talk about temperature when the gas is very dilute, because I mean, it would feel cold to you if you were there, but the temperature is still technically large because the average kinetic energy of the gases is big, but there's just not a lot of gas, right? It's a very dilute gas, but the particles are moving very fast. So the temperature...
So what you're feeling is the low sum.
Yeah, exactly. So the temperature's high, but you don't get hit by gas very often. So you feel the low sum and you get cold. So anyway, temperature is not a very good statistic to use when your gas is dilute. But okay, nice. So
And an aside.
yes. So anyway, this is good. As we said in its approximation, but in science, you always want to iteratively refine your approximation. So if you were studying the atmosphere, you would probably start with something like this. And then if the temperature effects are important, you would modify this equation to account for the effects of temperature. Then you would have something like, the environmental lapse rate or something, where you assume that the temperature drops off linearly, which is also an approximation. It's not actually linear, but it's a good place to start. And if you need the nonlinear effects, you keep making it more complicated. But this is a very common occurrence in science, where there's a trade-off between the accuracy of your equations and the simplicity of your equations. This is very simple. It's just an exponential of some number. So it's easy to understand, it's easy to graph, it's easy to derive, and it lets us think about it very deeply. But it's less accurate. The equations that are more accurate become very ugly. So they're just harder to think about, harder to understand. You can't solve them by hand, so you have to put them on a computer, but they're more accurate. So you always have to key the balance between accuracy and complexity for the criteria that you care about in the problem at hand. So it's something of an art. But okay, so we've been going for 2 hours. Maybe we can do the rest of this next time. The remainder is going to talk about heat engines. So how do you use an engine to do work with a gas? Well, you have to have your engine put in some heat at one place and extract some heat at another place. And then you find the integral of pressure d volume, which is the area under the pressure volume curve. And then you go around a circle in that curve and get some total work or whatever. And that work will be positive, so you can basically turn a heat difference into useful work. But that would probably take another half an hour, and probably don't want to do that. So next time.
Yeah.
Good. Questions on